Hi kids. I went over this paper yesterday in class and I made a video of it and I watched a little bit of it and I hated it. Um, just because, I was moving all around the room, so the audio was cutting out. And it was like almost an hour long, so I just kind of thought I would write up the test again and just kind of go through it quickly so the video can be shorter and there won't be any evidence on the video of me bullying Jimmy James. All right, so let's go. All right, so part A, you're always going to be doing an analysis of some kind of data. So these are questions that all the students will answer all over the world. All right, so take a minute, pause the video, and kind of read the heading here to see what we've got. All right, so first of all, we're going to be titrating acid with a base, and when they measured the volume of the base, they used a graduated cylinder. All right, so one thing you got to know is that, if you have to use a graduated cylinder, whatever, but they are really not the best for precision. So if you want better precision, you got to use something else. We'll talk about that. All right, so it said they were measuring the volume of the acid added to the base using a pH probe, but one group accidentally used a temperature probe. So we have their temperature data. All right, so on the graph here, we have temperature on the Y, volume of acid added on the X. You can see as the acid is added, the temperature increases, and we have some points here labeled A, B, C, and D. All right, so the first thing it asks is to calculate the percentage uncertainty for the volume of the sodium hydroxide solution. So the percent uncertainty is the uncertainty over the measurement. There's the uncertainty, there's the measurement. Don't forget, if it's a percentage, they want you to multiply it by 100. So the uncertainty over the measurement times 100 equals 2%. And suggest how the precision of that volume measurement could be improved. Again, you could use a volumetric flask. A volumetric flask is essentially without uncertainty because it only has one marking line. And the neck of the volumetric flask is very narrow. So you get a very dramatic meniscus, and it's really easy to measure the exact volume to the drop. If you use a burette, remember our burettes measure out to 0.1 milliliters, so you actually get a volume measurement with your estimated digit in the hundredths place. So it certainly would be worth taking the time to use a burette because it would be 10 times more precise than the graduated cylinder used here. Since the uncertainty is 0.5, it tells you that each line on the graduated cylinder was 1 milliliter. All right, so deduce why more heat was produced in mixture B than A. Well, this is a neutralization. It's an exothermic reaction. So as more of the reactants are reacted, more heat is released. So the reaction, it's exothermic. More bonds have been formed. Remember, bond forming is the exothermic part. So I just made it a little bit more specific by saying more bonds have been formed. So more heat's been released. And it says deduce why the temperature is higher in mixture C than D. Well, since it's an exothermic reaction, as it goes on, the temperature increases. So once you see the temperature begin to decrease, that tells you that the reaction is over, right? So once the reaction is over, cooling will begin. Heat will be lost to the surroundings, so the temperature will decrease. And then it says suggest how the end point might be estimated from the graph. Well, the end point, we usually use an indicator to tell us when we get there, but also if the temperature rise stops, then that also tells us that the reaction has completed. So we can just record the maximum temperature, and the volume of acid required to reach that temperature will tell you what the end point is. Down here it says state and explain how the graph would differ if we used 1 molar sulfuric acid instead of hydrochloric. Well, remember, hydrochloric is HCl and sulfuric acid is H2SO4. It's a diprotic acid. I gave a little bit of extra information here that you probably don't, but if you've got time, you may as well give as much information as you can. Now, try to answer the questions completely the first time, and if you have time at the end, go back to add details. But make sure you just provide as much as you can because you just never know if the thing you're going to say will be the thing that's correct. So I said for every 1 mole of HCl, we make a mole of hydrogen ions. And for every mole of sulfuric acid, we make double. So half the volume of acid will be needed. If it says state and explain how the graph would differ, I would say the endpoint would be at half the volume. But I think I probably gave enough information there. So then it said the graph of temperature against a titer. Titer is just what the volume you're adding, can be used to calculate the concentration of the alkali, the base, without knowing the concentration of the acid, using enthalpy of neutralization instead. All right, so the key here, since there's really no one equation to use to answer this question, the best thing to do is consider what you've got and consider what you need to get to. All right, so the first thing I thought, well, if we're recording a temperature increase, then we can use Q equals mc delta T to find out how many kilojoules of heat were evolved. Now, enthalpy of neutralization, whatever the value is, will have a unit of kilojoules per mole. Now, if we want the concentration of the base, you should know that we need the number of moles of that base divided by the volume of that base solution. So if I have kilojoules per mole and kilojoules, well, if I just take the value for Q and divide by the value for delta H when the units combine, that'll give you moles of NaOH. Now, I got the lowercase n here because moles are always denoted with the lowercase n. So you could have either said write out the MOL or just the n, and so that gives us the moles. The volume, we were told on the first page, is 25 cubic centimeters, which would be 0.025 cubic decimeters. I don't know if you need to give this level of detail, but couldn't hurt. So B says heat loss would make this method less accurate than the pH probe. Outline why this method would always give a lower, not higher concentration. Well, because that heat loss is occurring, the change in temperature would be smaller. You wouldn't measure as high of a maximum temperature because heat is lost instantaneously once the reaction begins. That means the value for Q will be smaller. If the volume for Q will be smaller, then the amount of moles will be smaller. And if the amount of moles is smaller, the concentration will be smaller. It suggests how we could reduce the heat loss. We use a more insulated container. Think a styrofoam cup. They call that polystyrene in Europe, but styrofoam, or throw a lid on the container. If you have access, use a bomb calorimeter. All these kind of things. Suggests why scientists make. Oh wait, I missed a question. And then here's a state one assumption. Other assumption that's usually made in the calculation that use these Q equals mc delta T calculations, we assume that the specific heat of the solution is equal to that of water. We also assume that the density of the solution is equal to that of water. The last thing, we assume that the specific heat of the calorimeter is negligible, so that the calorimeter does not lose or gain any heat during the process. And then why do we make these assumptions? Well, if you want to really investigate something, it kind of helps to do some experimentation in a more simple way beforehand, right? So if we make these kind of assumptions, it can help scientists understand a trend before investing in it further. And finally, outline why this method would not be good for a 0.001 molar hydrochloric acid solution. Well, that's the title page here. The concentration of HCl was 1, right? So that is 1,000 times less, which means the mass is 1,000 times less, which means the change in temperature would be way too small for the temperature to measure. All right, on to the actual option. All right, so carbon is produced by fusion reactions in stars. Outline how the spectra of light can be used to detect the presence of carbon. So remember, we use absorption spectra. I'm having a little trouble spelling that word. I think it's with the P-T-I-O-N, but whatever. Anywho, because there are two different things, absorption and absorption. I don't know. Who knows? Anyhow, so we use the absorption spectrum. So each element has its own unique absorption spectrum. Think of it like a fingerprint, right? So if we see the absorption lines that correspond to carbon's lines, then that tells you that it's there. Right, so the main fusion reaction responsible for this is some element being reacted with, combined with helium to make carbon-12. So remember, the mass and the atomic number on both sides for all particles will be equal. So we got a total mass of 12, which tells us the mass number of X is 8. Carbon has an atomic number of 6. These two have to combine to 6. Since helium is 2, it must be atomic number 4, and that is beryllium. All right, so here we've got the E equals mc squared calculation. It says the mass of this isotope is that, and the mass of helium-4 is that. Determine the energy produced in joules when one atom of carbon-12 is formed. All right, so remember, when we do these, that the mass of the product will be slightly less than the mass of the reactants. That missing mass is converted to energy, and that's where we get the energy from. So all I have to do is add the mass of this and that and subtract the mass of that. So that's what I do here. We got the mass of the beryllium-8 plus the mass of the helium-4 minus the mass of carbon. Now, if it's carbon-12, it's the standard, so it's exactly 12. And when we do that, we get 0.007908 atomic mass units. When we plug into Einstein's equation, it has to be in kilograms. So the conversion from AMUs to kilograms is in section 2. When you do that, you get 1.313 times 10 to the negative 29 kilograms multiplied by the speed of light squared, also in section 2, and that gives you the energy. Now, just a note on sig figs, we had to use all of our sig fig rules here. All right, so when we're adding and subtracting these values, I had to count the number of decimal places in each number and round to the correct number. So the carbon, I just kind of did a random number of zeros, but these were the ones that were measured. So 1, 2, 3, 4, 5, 6, 6 in both, so 1, 2, 3, 4, 5, 6. All right, then when I converted to kilograms, I multiplied using this number. This number has 1, 2, 3, 4 significant figures, so the mass was rounded to 4 significant figures. Now, when they multiplied by the speed of light in the mark scheme, they reported the answer to 3 sig figs. I think they're counting the sig figs in the speed of light. It is a constant, but it's not a universal constant, right? The 3 times 10 to the 8th meters per second is a constant in a vacuum. Light changes speed when it goes through different media. So I think that's why they added those for the sig figs, but whatever. All right, so nuclear fusion is very promising. What are 2 advantages over nuclear fission? So one important thing is that when fusion reactions occur, there's no radioactive waste produced, and you get a lot more bang for your buck in terms of mass. So a lot more energy produced in fusion than in fission. If you think about it, we fuse hydrogen, which is the lightest element. We get way more energy from teeny tiny elements than we do from the big ones. All right, class will be starting soon. So for this one, I'm not going to pull out the data booklet, but if you want to see what I'm talking about here, you can turn to yours. So this is about the dye-sensitized solar cell. It's also known as a great soul cell. Right. It says, identify 2 ways in which the structure of this dye resembles chlorophyll. So if you look in the data booklet, you'll see in chlorophyll you have a magnesium ion that has coordinate bonds in the center of the structure. So I just said both contain metal coordination bonds. Remember, coordinate bonds are when the ligand attaches to the transition, or actually I should say the metal cation, because magnesium is not a transition metal. And if you look in both images, all the metals are both bonded to nitrogen ligands. So any reasonable differences would work. Just make sure that they're actually there. So both photosynthesis and this cell use energy from sunlight to bring about reduction. Deduce an equation for the reduction reaction in the electrolyte. So what you need to know is that in the DSSC, the electrolyte is just the same reaction reversed between I3- triiodide and iodide. So if we reverse this arrow, it would be the oxidation of iodide to triiodide. Since it wants the reduction, we show the reduction process. All right, so now it's on to transesterification. It says vegetable oils require conversion to biodiesel for use in internal combustion engines. State 2 reagents required. So if you look in your notes, you'll see it's just methanol. You could use ethanol as well, and strong alkali. The example in the notes is sodium hydroxide. Deduce the formula of the biodiesel formed. Remember, we're just going to break this 3-carbon chain off and replace each of those bonds with a methyl group, making them methyl esters. So pretend that there's an H there. It would be H3C, CH3, right? Methyl group at the end. And then we have the OOC, and then the CH216CH3. So we're just taking each of these and making them individual esters. The other product that would form the OH groups from the base and from the alcohol will add to this 3-carbon chain to make glycerol, which would be CH2OH, CHOH, and CH2OH. All right, I'm going to move a little faster now because class is starting. All right, determine the specific energy in kilojoules per gram and the energy density in kilojoules per cubic centimeter of a particular biodiesel using the following data in section 1. All right, so section 1 just tells you that tells you exactly what the problem does, that specific energy is energy per mass and energy density is energy per volume. What I told you in the class was a little bit simpler. If you want specific energy, it's just the enthalpy of combustion divided by the molar mass. And energy density was the enthalpy of combustion times the density divided by the molar mass. Now the only thing where you might get tripped up is the units here. So we need to be working in kilojoules because we need kilojoules per gram and kilojoules per cubic centimeter, but we are given megajoules. So remember, a megajoule is 10 to the 6th. A kilojoule is 10 to the 3rd. The difference between them is 10 to the 3rd, so 12 times 10 to the 3rd is the number of kilojoules. All right, so here we just divide it by the molar mass. Here we multiply it by the density, then divide by the molar mass. 21 says coal is often converted to liquid hydrocarbon fuels. Through initial conversion to carbon monoxide and hydrogen, state how these gases are produced and give the appropriate equation. So 2 marks, 1 for the stating, 1 for the equation. So what you need to know is that when they're doing the gasification reaction, they pump air and steam down into the coal beds. So they heat those coal beds with air and steam. So coal is almost entirely made of carbon. When it reacts with the steam, it makes the carbon monoxide and hydrogen. Excuse me. You could also add the oxygen in here. It just makes the balancing a little bit more complicated, but either one would be fine. So outline how the carbon monoxide is then converted to hydrocarbon fuel. Well, remember, in society, when we're using hydrocarbon fuels, we use liquid fuels. Liquid in the butane lighter, gasoline is liquid, kerosene, all liquid fuels. So this is about liquefaction. So when we do the liquefaction of carbon monoxide, we react with hydrogen, I think, over a platinum catalyst. Again, it's 1 mark. It's better to give more information than less, even if it's incorrect, because if you say the correct thing, you still get the mark. Just make sure you don't fall into the trap of doing that all over the place, because then you'll run out of time. So react with hydrogen, I know it's the Fischer-Tropsch process. So I show carbon monoxide reacting with hydrogen to produce octane, which is a liquid fuel, plus water, and then the coefficients are just for the balancing. All right, as well as being burnt, methanol can also be used to provide electricity through a fuel cell. Deduce the half equations for the reactions occurring at the 2 electrodes and hence the equation for the overall reaction. Well, we have a diagram here, so even if you don't remember what all the parts of this are, the diagram tells you. So at the anode, that's where oxidation will happen. So methanol and water go in and are oxidized to form carbon dioxide. So these are my reactants, that is my product. So the oxidation half equation is methanol plus the water making the carbon dioxide that forms, and when we balance, I have 6 hydrogens over here, so I have to balance with 6 hydrogen ions and ultimately 6 electrons. Now at the cathode, we see that the reactant, the oxidant, the thing that is going to be being reduced is air, and it's the oxygen in the air that's reactive, not the nitrogen. So oxygen will react with the hydrogen ions passing through the proton exchange membrane to make water. All right, so when we balance, since we have it was O2 plus H plus, but then I had to balance the thing. I'm sorry, I lost my train of thought. I'm getting distracted. Anyways, you can always check to see that these are balanced because all the elements and the total charge should be balanced. All right, so when we combine to get the overall, A couple ways you could do this, as well as being burnt, that refers to the enthalpy of combustion of methanol. You could just write the methanol combustion equation and balance it, or you could use your equation. So I got 6 electrons. I'm pointing at the screen with my finger. You got 6 electrons up here and 4 down here. You could do 2 things. Basically, the thing we have to do is make it so the number of electrons in both half equations is the same. So I can multiply the anode equation by 2 and the cathode by 3 to give 12 electrons to make them cancel out, or you can just multiply the cathode reaction by 3 halves and that'll do the same thing. So when you multiply by 3 halves, that gives us 6 electrons in each equation, so they cancel. It gives us 6H plus in each equation, so they cancel. It gives us 3 waters in this one, but that 1 water up there cancels 1. So when you bring everything else down, you get methanol plus 3 halves O2, makes CO2 and 2H2O. If you do it the other way, where you double that and triple that, it would be just everything would be double, right? So 3 halves is 3, 2, and 4. All right, almost there. Even though fuel cells, primary cells, and rechargeable cells have similar characteristics, there are important differences. Suggest the way in which they're similar. They're all examples of voltaic cells, so they all convert chemical energy into electrical energy. Outline the difference between primary and rechargeable. Well, primary are one-use batteries because they use non-reversible reactions. Rechargeable batteries use reversible reactions, so you get multiple uses out of them. Identify one factor that affects the voltage and a different factor that affects the current it can deliver. So in general, you could probably just say the chemical nature of the electrodes. You could be more specific, so you could say the identity of the electrode, or you could say the temperature of this electrolyte, or the surface area of the electrodes, mass of the electrodes, etc. For current, it's all about the resistance that we get in the cell, which of course is limited by the ability of ions to move around in the electrolyte. All right, so suggest why in only recent years we can make specific predictions about the future effects of fossil fuel combustion. We've known about climate change for over 100 years. We've actually known about the absorption of infrared radiation by polar bonds in carbon dioxide longer than that. But why in only recent years can we make predictions about the future? Well, the big thing, advances in computing power, allow really, really complex systems to be modeled. The Earth's climate is extremely dynamic. So 1960s computing power couldn't quite make the calculations it needed to make, but we can now. All right, and finally, last page, carbon dioxide has 2 different stretching modes. So we could do symmetrical stretching and asymmetrical. Remember, in order for the stretch to cause the absorption of infrared, there has to be a change in the overall polarity of the molecule. So if we stretch these symmetrically, the overall molecule, it does change the individual dipoles, but because we're doing it symmetrically, it doesn't change the polarity of the molecule. But if it's asymmetrical stretching, as this bond decreases, it changes the polarity, so yes. Outline giving the appropriate equation or equations, how increasing levels of carbon dioxide will affect the pH of the ocean. You know, one thing I might want to say here, just in case, show the equation where aqueous CO2, when reacted with water, produces hydrogen ions and the hydrogen carbonate ion, but you also might want to say pH decreases. It's probably not required, but just in case. And then finally, many combustion processes put particles in the atmosphere. How might that affect the temperature of the Earth's surface? Well, those particles can absorb or block sunlight. They could also cause increased cloud formation, because clouds form when water molecules begin to surround dust particles in the atmosphere, and that will cause the lowering of temperature. So that's it. 24 minutes, definitely better, and I don't appear quite so crazy. All right, kids, thank you again for watching, and IB, if you want to ding me for copyright, this is, in my opinion, falls under fair use just because it's basically for the world, but only my students watch it. All right, have a good one.